Welcome to the TCS seminar at the Academic University. Today our speaker is Hoang. Hoang was with us last year as a postdoc. Now he has a position at the Université Paris-Saclay. And the topic of today's talk is something about reconfiguring or reconstruction. Reconstruction, actually, of graphs, I assume, under some kind of queries that we will see. Thanks for coming, Hoang. The floor is yours.
Thank you very much for the introduction. So I was told that since I'm giving a talk in Poland, I'm obligated to make this joke. So from the picture, you can guess I'm working on the reconstruction, but of graphs. So for everyone else, which means non-English speakers, we'll move to something more like this. Okay. So today I'm going to talk about graph reconstruction, and then with, I guess, like an extra flavor added to it, which is connectivity queries. These I will explain in a moment. This was done with Kasper Gluck and Marta Piecyk, who are PhD students in Warsaw. Kasper is starting his PhD with Marcin Filipczuk, I believe, and Marta is doing her PhD with Paweł Janczewski. Right, so actually when we talk about graph reconstruction, for those who know it a little bit, you might think about this conjecture that I will present, right? So I'll just go on n graph, a graph on n vertices. So let's take this one on 4 vertices, for example. And from this, I can generate like a multi-set of n-1 subgraphs of this graph. So I just remove one vertex, I get some subgraph of it. And why multi-set? Because I can have multiple subgraphs that are isomorphic. Okay. Now let's say that I have this set of n-1 subgraphs. Can I rebuild the original graph? Well, in this case in particular, it's not that hard, right? You take one of these n-1 subgraphs, say, okay, I have n-1 vertices already. And then you can just do like check naively for the last vertex, which edges to add or not to obtain your order subgraphs, right? So this is the answer. And in general, this question is quite hard in a sense that it's still open. There's this conjecture by Kelly and Ulam made independently, I believe, in the 1950s that state that if n is big enough, here is just 3, then from this multi-set of n-1 subgraphs, I can always sort of rebuild my original graph uniquely. And I will explain why I added uniquely. Right, and why n at least 3? Well, this is simply due to the fact that you cannot distinguish between an edge and 2 isolated vertices, right? If you have n-1 subgraphs, you only get 1 isolated vertex. Right. So today I'm not really here to talk much about this conjecture, but something related to this. So let us change the setting a little bit. Imagine that I have labels on my graph, right? Okay, so I have vertices 1, 2, 3, 4, and instead of seeing the set of n-1 subgraphs as something that was given to me, I will say that I have some oracle that I can query, and it will give me some graph that is isomorphic to the subgraphs that I'm querying, right? So let's say that I'm querying n-1 subgraphs. So when I ask for 1, 3, 4, it answers this first graph, 2, 3, 4, and so on. So actually, this setting is exactly the same as the last one. Why? Because I can always assume that my graph is labeled in a certain way. And this multi-set of subgraphs, I can always assume that the first one is by removing the first vertex, second one is removed by removing the second vertex, and so on. So I have some labeling of the graphs too, and these are the answers to my queries. So of course, if I can solve this problem, I will be able to solve my original problem. Okay, so this is still hard, right? But what now, instead of querying only n-1 subgraphs, what, right, okay, so this is a new question now, just rephrased. But what if I can query k subgraphs instead? So instead of k being n minus 1, say, what if I can query for k equals 2, right? For k equals 2, this is very easy because it will tell me directly if I have an edge or not. And so I can rebuild my graph quite easily, right? So for k equals 2, it's easy. For n minus 1, we don't really know what's the answer. So is there some sort of threshold, at least like for which the problem is quite easy to solve? Now I will show you that actually starting from k equals n minus 2, this is already very easy to solve. And I don't even need all of the information given to me by this like the answer to the query is some graphs that I'm isomorphic to. Well, I only need like number of edges in this subgraph, for example. And so this is what I will prove in a moment. So let's say that n is at least k equals k plus 2, okay, and this is at least 4. For 3, you can check that it works out well as well. And I can rebuild basically any labeled n graphs by doing these queries on k subgraph. Yes?
You are asking those queries one after the other, after getting the answer, or simultaneously?
Okay, yeah, there's two settings. You can see it as I have all the queries I want, and now can I rebuild the graph? Or I can also say that, oh, maybe I want to optimize the number of queries. Here, I'm just assuming that I have all the queries that I want. Well, for number of edges, you don't actually need all of them to rebuild the graph. But soon I will talk about other type of queries for which if you don't have all of them, then you cannot rebuild the graph. Right. Okay, so let's try to rebuild something just from the number of edges. The first thing I can say is that, okay, let's take some subgraphs big enough, well, at least of size k. I'm trying to count the number of edges in this subgraph. So I start by doing something quite simple. I just sum up all the number of edges from the queries that I obtained from the subgraph, right? Okay. Now, like how many times do I actually count an edge here? So an edge, if you fix one, right, little counting exercise, then you can choose the other k minus 2 vertices from the h minus 2 remaining vertices, right? So every edge here appears exactly size of h minus 2, choose k minus 2. So I just divide it by that, and I get my number of edges in h. And once I have this, then it is quite easy to check when do I have an edge between two vertices. So I have some indicator function. And let's say that I start from just total number of edges of G with this added number of edges of G minus U minus V. So I remove UV and I added this extra number of edges on top of it. Okay, so this counts this number of edges in this graph of mine. And now I can remove the edges in G minus U and then the edges in G minus V. And the only thing that remains will be 0 or 1, which is either there's an edge between U and B or not. Right? And here you can see that where do I use the fact that n is at least k plus 2? Well, this is because I needed G minus U minus V to be of size at least k. So already from n at least k minus 2, I only need number of edges to be able to rebuild my graph uniquely. Now you might wonder, okay, maybe this approach can work out for k plus 1. Well, of course not, otherwise this question would have been solved already. So why does it not work, right? So if I only get number of edges, why can I not rebuild graphs of size k plus 1 in this unique fashion? Well, here's an example. Take these two graphs. You have in the first one, just 2 clicks of size k plus 1 over 2, and then I add a matching between them. And you compare this to just this complete bipartite graphs with, again, k plus 1 over 2 vertices on each side. Now, what happened when you query a k subgraph of this thing? Well, it's the same thing as removing one vertex, and all of these vertices have the same degree. So you're removing always the same number of edges, which is something like k plus 1/2. And so these two graphs clearly gives the exact same queries, yeah, for every case of graphs. And also, of course, they're different. I mean, on the left, I have very big cliques, and on the right, I have a bipartite. Okay, and so this only works for k odd, of course, but if it's even, you just add one universal vertex, and you can check it by yourself, but it works in the exact same way. So, of course, querying only number of edges do not allow me to solve this conjecture. Okay, so the idea here was that I'm not asking for graph isomorphism. I'm only asking for some parameter of the graph. So we can see that if I have a number of edges, then the problem becomes quite easy. But what if I have something that gives me a lot less information about the graph? For example, a natural query that we actually studied in this paper that I'm going to present is connectivity queries. So what does it mean? It means that I query a k-sub graph, and the oracle is supposed to say if this subgraph is connected or not. So induce subgraph. So I'm giving it a set of vertices. Says the subgraph induced by the set of vertices is connected. Right. So once again, for k equals 2, this is easy because two vertices being connected just mean there's an edge between them. Disconnected, there are no edges, right? But already for k equals 3, we might have some problems. First thing we can see is that, let's say that my graph is not connected. I have just a bunch of little components like this, like a matching, let's say, right? And I compare this to just an independent set. Well, every query will answer disconnected, right? Because I'm taking set of size at least 3. Okay. So maybe we only look at connected graphs right now. Whilst I also have this sort of problem is like, okay, these 3 vertices are connected, but maybe there's a triangle, maybe it's just 2 edges. Like, how do I distinguish between them? Okay, now maybe here you'll tell me that, okay, but this is too small. Maybe it will work if the graph is big enough, right? Well, here I have another example. Let's say I have this sort of caterpillar-like path, and then I can add an edge between any of these vertices here, right? And I cannot distinguish between this thing and that thing, right? And here you can imagine any sort of combination of edges or not. So this increases exponentially. Right? I have an exponential number of graphs which answers the same to these queries. All right, so already with 3, the problem is not that clear. So here, what can we do? Well, we might not have this sort of unique reconstruction property, but we can imagine that given a set of queries, I mean, answers to these queries, can we just maybe enumerate all of the graphs that correspond to these queries in a reasonable time, right? Let's say polynomial in the size of the output. And because size of output here can be very big. And so, yes, so there exists an output polynomial time algorithm to determine every connected graph consistent with some given set of queries. And this was already answered, actually, and this is actually the paper that introduced this setting of graph reconstruction with connectivity queries. And of course, they prove a lot of other things. But for this in particular, it's very easy. For this algorithm, what they're doing is that they're translating this to 2 sets. Okay. So how does it work? Let's say that I query A, B, C, 3 vertices, and it answers connected. If it is connected, what does it mean? It means that if I take any 2 edges, any pair of edges, then at least one of them must be there, right? If they're both not there, then I'm disconnected, right? So I can write this in terms of set formulas where my literals correspond to the presence of an edge. So I can translate this to, either AB or AC must be there, NAB and BC and so on. And it's the same idea when it enters disconnected. So I transform all these into two SAS formulas. And first of all, I can have existence in polynomial time, but actually there's also an algorithm to enumerate all of the solutions in output polynomial time. So I'm not going into the details of this algorithm, but I'm just showing you this because somehow here you sort of feel like, oh, okay, so what if I try to do this for bigger K? Well, it doesn't work, right? Of course. Here you have two sets because you take pair of edges and you say one of them must be there. Now, already for K equals 4, if you try to translate this, then you're already getting something like 3 sat, right? And okay, unfortunately, 3 sat cannot be solved in polynomial time. Well, who knows? But as far as we know, this is not possible yet. And so there's sort of this feeling that, oh, this problem might become hard. Even just existence might be hard from K at least 4. Right, so here we're not even asking for an enumeration algorithm, we're just asking for existence. Is there a graph that is consistent with a given set of queries? Unfortunately, we did not manage to prove that this is NP-hard. We only proved this for a variant of this problem where you don't have all the information. I say that your oracle is allowed to answer, I don't know, for some of them. So in this setting, where you lack some information, we can basically reduce 3 sat to this. And today I'm not going to show you this reduction. It's quite an easy one. Maybe you'll actually be able to find it yourself in an afternoon. And I'm not showing it because I don't feel like these ideas can be generalized to solve the setting with complete information. But let's say that we do believe that this problem is hard. So that's why we're trying to look into more specific graph classes of graph. Now, before moving on to these specific classes, I will try to explain why we're looking at them. So here are some obstructions, quote-unquote obstructions for this problem. What happens when you have twins in your graph? Meaning that you have vertices which see the exact same set of neighbors. I mean, excluding themselves. Then here, whatever you query, right, you cannot know if there's an edge between them or not. Okay, so this is sort of something that can sort of hide information of your graph. Now, there's another thing that also kind of hides some structure of the graph is, we talked about this thing with these small components, right? Like, okay, I cannot distinguish a graph which is composed of only small components in an independent set. And that's why we're looking at connected graphs. But what if I just cheat by saying that, okay, now I add the universal vertex. So now the graph is connected, but still I cannot determine these small things at the tip of this star, right? So if I have a very high degree vertices, and here I hide some edges here and there, so that I don't have a big component. If I query something that contains the center of the star, then it's always connected, so it does not give me information on these edges. And if I query only the tip of the star, which means these vertices, then maybe since there are only small components, I also do not know if there are edges there. So these are like sort of the two obstructions that we found that's really hard to overcome, let's say, in this problem. And that's why our results center around first triangle-free graphs. So what happens in triangle-free graphs? If you have twins, then there's no edges between them because I don't have triangles. And it's the same thing. If I have a star, then also I don't have edges or anything at the tip of this star. So here it clears both of the obstructions, and this gives us an enumeration algorithm in a reasonable time. And even better than that, we get uniqueness actually. So you can really see that these are really like the main obstructions for this sort of problem. If you manage to clear them, then somehow you get uniqueness, right? This is our intuition behind it. Now, there's also another thing that we looked at, which are graphs of bounded maximum degree. Well, the idea is that, sure, you don't have uniqueness, but these, for example, these high degree vertices cannot be actually very high degree, right? You have bounded maximum degree. And so you have some sort of these structures that hide information in your graph, but these are bounded of constant size. So maybe I can still deduce most of the graph, and just for some part of it of constant size, let's say that I can do something naive like enumerating all possible subgraphs. So this is the intuition behind it, and it does actually work out. So we also get an enumeration algorithm for graphs with bounded maximum degree. Okay, so that's pretty much our motivations, and that's why we came to these results. Now let's actually try to see some proofs.
For any k.
Yes, for any k.
The bound on the degree.
It's just any, yeah, so it will depend on k and d, let's say, which d is like the bound on the maximum degree. So yeah, for fixed k and d, let's say, then it's polynomial. Right. So first for triangle-free graphs, let me recall the objective here is just to enumerate every connected triangle-free graph that is consistent with our set of queries. Now, our strategy is quite simple. We will build a layering of G. So layering here just means that I partition my set of vertices into layers, and edges only live inside a layer or on two consecutive layers. So sort of you can think of VFS layering. And actually, this is exactly what we will do here. Okay, so first, actually, let's start with this case where we have some big vertex. So here I just took a concrete example. Let's say k equals 4, but this proof generalizes to every k. And then I have some vertex with at least like six neighbors. So I'm saying that if this vertex lives somewhere in my graph, then I can find it, determine it exactly its neighborhood, and build this layering and so on and so on. So how do I actually do that? So assume that I have such a vertex somewhere in my graph. Now, the thing with this in a triangle-free setting is that whenever you query some set of vertices that exclude this vertex, then must answer disconnected, right? Because if these are my neighbors and I'm supposed to be triangle-free, then this is an independent set. And if you query anything that contains this vertex, it must answer connected. So this is more or less a star. And I'm going to show you that the star is the only thing with these sort of queries.
So you assume that you have a universal vertex?
No. I just say that I have some vertex with big degree. So let's say that here's like 6, right? At least 6, I mean. So I just take a look at every set of 7 vertices on my graph, and I look for these properties. That there's a vertex for each query of 4 vertices is gets connected, and each query that does not containing this vertex gets disconnected. And I say, if I have such a thing, then it must be a star like this. Okay, so how do we show this? Now imagine that, okay, I have such queries for this set of 7 vertices. And okay, maybe some of them is actually not connected to this big vertex. Well, I cannot have too many of them. In this case, I cannot have 3 of them, because if I do, then this cannot be connected, right? This query cannot be connected. So I have at most 2 of them. And now what happens here? Let's take a look at, like I take one of these 2, let's say, and 3 other vertices. I query this. This is supposed to be connected, but since it's not connected to the center of this star, then it must be connected in some other way, like this. Okay, and then I can do the same for any other set of vertices that are actually connected to my vertex. And if this set is big enough, and this is where I use the big enough, then at some point, I guess I get this query, right, on the supposedly neighbors of mine, but it gives something connected, right? But this is a contradiction, of course, because in this set that I found, anything that excludes this vertex returns disconnected. So actually, the star is the only thing that answers with these types of queries. So anytime that I have such a vertex with enough number of neighbors, then I can determine it exactly. Right? Okay, and from this, it's easy to see that you can determine the rest of its neighbors, of course. These are already your first two layers. Right? And of course, now, once you have this, then you can determine the vertices in the next layer. Anything that is connected to this thing has to be connected through one of these neighbors, so they are in the second layer. Now, to determine the edges between them, we have to work a little bit. Let's say that I look at these four vertices, and it returns connected. Well, it's easy. The only way this is connected is by having a star like this, because x2, 3, and 4 form an independent set. Okay, now I have another type of query, which is like this. Like if I query this vertex, two neighbors, and U, then what I'm saying here is that what am I saying? I'm saying that, okay, if I have vertices of the first type, it's easy to determine its neighborhood, right? They say it can have more neighbors, but I just add all of them one by one. So if I have a vertex with not too many neighbors, let's say the second one does not have too many neighbors, here many neighbors just mean 3, then I can actually find a pair of vertices to which is not connected to. So something like this. And once I have this, it's pretty easy to deduce the rest, because now I just look at these one by one. I know that this is not connected to x1. So if this is connected, it must be connected through x3. If not, then I have another non-edge, and so on. And this is how I deduce the rest of my edges. And once again, here I'm using the fact that I have a sort of a big enough neighborhood in the beginning. Yeah.
So I missed the point, how do you deduce non-edges?
Okay, so here I'm just saying that either I have vertices of this first type, which have enough neighbors. So I'm just querying this vertex and some vertices in my first layer. And I mean, if it returns connected, then I have this, right? And if it has more neighbors than that, I can just continue doing that. For those vertices that do not have many neighbors, then I just say that I choose, my first set is large enough so that I can always find such a pair of x1, x2 that is not connected to this. So I just go through all my queries until I find such a pair. And this pair must exist. Otherwise, it means that this guy has a lot of neighbors and it falls into the first category. So you establish non-edges. Exactly. So once I have some non-edges, then it's easy to continue. And this is where I use also big enough. So now I managed to deduce these first two layers, and this is really the hard part of the problem. Once I have this, it's pretty easy to deduce the rest, because now I just, okay, for k equals 4, 2 layers here is enough. You can see I take these 3 vertices and then just look at stuff that is connected to this, and I would get edges between my second and third layer. And for bigger k, actually, we don't need more layers. We can do this sort of thing, because here I'm only taking vertices in the first layer. I know they will not be connected to the third layer anyway. So the only way it is connected is through this vertex in the second layer. Yes. So still with this assumption that U has big enough neighborhood. So actually, you just need to sort of really fight for the first 2 layers, and then you're almost done. And with this, you can deduce all the edges and all the layers for the rest. Now, what is missing? The thing is that is missing are the edges inside one layer, right? Now, for triangle-free graphs, there's an easy configuration, which is this one, where two vertices have a same neighbor. Then, since it's triangle-free, there's no edges between them, so there's no need to do anything. And if they do not, then I can do this sort of thing, where I take like x6 here is like the neighbor of one, but not neighbor of the other. And again, I go back to U to have a big enough set, and then I can see if this is an edge or not. This is for k equals 4, and for bigger k, we can do also this sort of trick where I just take some number of neighbors that are not connected to this other vertex. I can always do this by taking the vertex with higher degree. And again, I'm relying on the fact that I have chosen like a big enough neighborhood and everything.
But this guy on the right could have also a large neighborhood.
Yes, but the thing is that if the neighborhood intersect, then there are already no edges. And if they don't, then I'm just saying that this is big enough so that I have at least k vertices. Yeah. Right, so with this, I'm done. I managed to do everything. And the thing you can notice here is that actually I only needed this assumption that I have these 6 neighbors. And once I have that, all the rest is determined uniquely, right? There's no other way to do this. I mean, to answer to these queries. So I almost have uniqueness with my algorithm. There's still this other case of what's happening when I actually don't have any vertices of high degree, okay? In this other case, and what do I do? Well, let's say I just start with some subset of size k that induce a connected graph. And here I'm just guessing randomly. I'm just going through the to the k choose 2 graphs, I guess. And then I'm just guessing that this one of these graphs. So I have like a lot of instances of my algorithm running at the same time. So I'm just choosing some random graph here to start with. And since I have bounded degree now, I know that this first neighborhood also has bounded size. So, okay, actually here the big enough is 3k minus 6. Anyway, just some constant depending on k. And even in these first 2 layers, basically I can just guess every edges. And I'm allowed to do this because this is of constant size. So going through this, even going through every graph is still of constant size. And actually, when I have these 2 layers, the rest of the algorithm is exactly the same. Yeah. So for each of these random guesses that I made, the rest is unique. So only the part that killed my uniqueness in this algorithm is this thing where I have random guesses at the beginning. So I'm not actually going into the uniqueness part.
So where do you use the assumption that you start with the connect?
Where do I use this assumption? I mean, I guess our algorithm would work for if like every component is.
No, but you say that you are guessing that some subgraph is connected.
Yeah.
Which one, L0 or?
Both L0 and L1. I mean, you can determine L0, and then you can guess, not guess, but like from your queries, you can get the vertices of L1, and then you guess the edges inside L1. Why? Because like we needed
L0 is a size k, right? So you said you're taking just anything that answers yes for this k subset, and then you know it's connected. And then you say that you're branching for all the cases of this subgraph on k vertices. Yes? And then for each case, you have a separate instance of none and
And then, I mean, from your queries, you can determine what are the vertices that are connected to L0 now. So these will give you the set of vertices for L1. Okay, now once you fix this, you branch again on the guesses for the edges of L1.
Okay.
Yeah. Okay. So yes, you can end up with some constant number of graphs that answer to these queries, but we actually show that there's only one of them. But this part of the proof is a little bit technical and not very fun. I don't feel like it gives much more insight about this problem. We're only saying that if the graph is big enough, then actually you can always determine it uniquely. Right. Okay. So I like this algorithm also because we are expanding on the same ideas for our other setting, which is bounded maximum degree. So let's keep this layering in mind and move on to the other problem, graphs with bounded maximum degree. So our objective is the same, enumerate every connected graph with bounded maximum degree, which is consistent with our queries. Now, my strategy will be to build something that we call skeletons. So what are these skeletons? To give you a sort of a intuition about this, so it will be some graph, I guess more like a partial graph. Partial graph here means that maybe some edges are unknown. And in this skeleton, I have these small sort of pockets of constant size in which there might be some unknown thing about my graph, but then for everything else, everything is determined uniquely. So to illustrate this a little bit further, let's take an example. So I'm going back to this example with sort of a very long path, just to keep it connected. And then I have these vertices of high degree, let's say. And at the tip of these stars, let's say that in this example, these three vertices here form a connected subgraph, right? And my problem is I really like any pair of two edges will give me a connected subgraph. So any combination of these will answer to my queries, which gives us this exponential number of possible graphs. But one thing you can notice here that in all of these graphs, I would like to have something like, oh, this green part is actually uniquely determined. And then the only sort of random variability here is in these red parts. But the size of these red parts are small, right? Because I bounded my maximum degree. And I also like another property of skeletons is that these red parts are not only small, but they do not interact with each other. Meaning I can do any combination of any graphs that answer to my queries in these red parts independently, and it will give me something that answers my queries. So this is the intuition behind this notion of skeleton. And the size of these constant part, we call it the width of the skeleton. So ideally, I would want to always be able to build a skeleton with small width. And in this case, with bounded maximum degree, actually the width will be exactly D, which is what we got intuitively from this example. Okay, so now this proof is a little bit more involved. And I hope that I will not lose all of you. Okay, so let us start with the first two layers. Again, here I'm just trying to get some polynomial time algorithm. And since I have bounded maximum degree, I can use my previous reasoning and say that I can guess just the first two layers because the size of these sets are bounded. And here I can, so okay, I might not get one skeleton, but I have a constant size family of skeletons. And once I have this, I can determine the set of vertices for the other layers and the edges between them using the same idea. So this is not too hard. Now let's go to the hard part, which is what happens inside a layer, right? Now inside the layer, I will define these red blobs as sort of maximal set of vertices that have the same neighborhood in the previous layer, right? So, for example, in this left one, maybe all of these vertices are connected to the same vertex, and on this right one, is the same two vertices. Okay. And these red blobs will be sort of these pockets where some random thing can happen in my skeletons. And now I want to show that anything that lives outside of this will be determined uniquely. Okay? So what happened to edges, let's say, inside a layer, but outside of these blobs?
Looking at the layer for this class over the neighborhood of the previous layer, and we just so these are like you will not investigate it in the edges there because this is the partition of the LI, and you just want to show us that you know the edges across these lines.
Yes. Okay. Yeah. So I will show this, and also it's a little bit more subtle than that because I am claiming that in my skeletons these sort of red blobs do not like live independently of each other. So a choice that I make in one will not influence a choice that I make in another. So this is not obvious yet. Right? Like, sure, I can determine these edges that live outside, but let's imagine that you have some K-subgraph that intersects multiple red blobs, right? So I want to say that even if it intersects multiple red blobs, it doesn't matter. Like,
so you have complete freedom.
Yes. So at some point, I will.
This freedom means that any kind of subgraph is possible there, or
no, not every kind of subgraph, but like, let's say that if I have a subgraph that answer to the queries that intersect these red blobs, then I know that this is a valid subgraph without looking at anything else. Yeah.
So some kind of product structure of the solutions.
Yeah.
Okay.
Okay, so right. So let's start with the easy part, which is determining edges that live outside of these things. Well, let's say that I look at this first case. It's like I say, it's between these two red blobs, and I will use the fact that they have this private neighbor kind of thing, right? They must have a private neighbor, otherwise they would be in the same blob. And I go down to this private neighbor, and then I go down a layer. And once I go down a layer, I know that nothing is connected to these things up top anymore, and I just take enough vertices. So this is why I sort of needed a starting block with enough vertices. And so, yeah, this query will give me if there's an edge or not, and let's say that there is. And here is the same, really exactly the same idea. I mean, I just drew two different edges, but it's actually only one case. There's always some private neighbor, otherwise they wouldn't be in the same block, right? Okay, so and say that we don't have an edge in the other case, right? Okay, so this is what actually I just talked about. Sure, we can determine everything else outside of these blobs, but why do I have sort of this freedom? And it's independent, each blob is independent from one another. Okay, imagine that I have some subgraph like this of size K that intersects multiple red blobs. And this is not even on the same layer, it could be like different layers, something you can imagine, anything. Right, this is where we introduce this notion that we call importance of some unknown edges, right? So this is a little bit more subtle because it depends on the subgraph, so it's important for the subgraph, and also it depends on the current state of the graph, right? On the partial graph, so on the current state of known and unknown edges. So let me try to explain this a little bit clearer. An edge is important when its presence like it being there or not, can influence the connectivity of my subgraph in the future. Okay, so let us take an example. Let's say I have 4 vertices. Okay, and let's say that this will return something connected. For now, all of these edges are important because say if one of them is not there, then who knows, like when my algorithm is running and I determine some edges, if I don't have this edge, then I might not be able to make it connected ever. Right? So all of them start out being important. And now I'm running some algorithm, at some point determine an edge, right? The others still stay important. At some point determine another edge. And now here what happens is that this edge here between these two vertices, well, it's not important anymore because anyway, they will be connected already by this other path. So it being there or not there will not influence the connectivity of my subgraph, whatever happens in the future, right? So at this point of the algorithm, in the current state of my partial graph, this edge becomes unimportant. Okay? Yeah, so you fix the subgraph and you fix the state of your current algorithm, basically. Okay, I didn't want to introduce too many formalism here, so this is just to give you the idea behind this. And then say at some point I determine another edge, so the other ones now become all unimportant because it's already connected. Them being there or not does not change anything, right? So why is this notion sort of important for our problem? Unintended. Well, what I will want to show is that actually all of the important, I will be able to arrive at some point in my algorithm. So I will build a graph edge by edge. And at some point of my algorithm, I will arrive at a state where all of the important edges for a certain subgraph will live only inside one of these blocks. All of the unknown edges for H outside of this red block will be unimportant, meaning that I don't care what they get assigned to. I only care about the unknown edges of H inside this red block. And this is how I get my freedom of choice here. Am I clear? So I'm just saying that I'm just running my algorithm, and at some point I arrive at some state where all the important edges for a subgraph lives inside one block. So each K subgraph gets assigned exactly one block where all of its important unknown edges live. Right? So the only thing that matters for its connectivity is the choice inside this one block. Right? Yeah, this red thing, yes. Okay. So how can we show this? Well,
so it must be in one block, or it could be in several blocks, which is one.
No, I mean, like, doesn't matter if it intersects like a ton of different blocks. I say that only one of them contains the important edges for this one. Like its edges in the others block are all unimportant, so I don't care what, like, it can be assigned to an edge or a non-edge. It will not change anything for the connectivity of H. Okay, so let's. Okay, so actually, how do I arrive at this state where everything important lives in one place? The algorithm is very simple. It's just basically determine whatever you can determine. Okay, and what does that mean? So I know that I've determined everything outside of these red blobs, right? What if I have an edge that lives inside this thing? Well, it would be nice if I have some subgraphs like this. H prime, let's say of the right size that contains U, but V is not connected to anything in H prime. Why is this nice? Because if I have this, then I can just query this, right? The only way this is connected is if V is connected through U, right? So if I have this sort of thing, then I just query this, determine if there's an edge or not, and I do this as long as I can, basically. So this is the idea of just determine whatever I can determine. So I run this through its course. And at some point, I cannot do anything anymore, right? And at this point, I'm saying, okay, now I'm done. Everything important will be in one place. And let's just see why that is true. So we have this sort of configuration. So suppose that it is not true, then I have these two different red blobs. I have some subgraph of size k, and I have two important edges of this subgraph living in different blocks, right? Okay, so I call them UV and XY. Now, the first thing that we should observe is that there must be some sort of potential path between U, V, and XY, right? Imagine that somehow my non-edges already determine like a cut between these two. I can never connect one with the other. Then they cannot be important, right? Because whether they are there or not, H is already disconnected. Yeah? So there must be a way to connect them somehow. Yeah? Maybe I have not determined this path yet, but there must still be a possibility, right? Like there cannot be only non-edges between these two, okay? So I have some sort of path, and you can imagine something crazy like this, for example. So maybe some edges are already determined, some are unknown, some unknown edges are important, some unknown edges are not important. Yeah. So we have something random like this. Now, first I want to say that you can see this edge down here, right? That maybe lives in another red blob, yeah? And that is also important. Well, I just say if there's such a thing, then I just look at, it will be my new XY, right? I can just look at this pair of UV and XY instead, or I look at the further one. You know? I can just take the shortest path such that I have these two important edges living in other stuff. Okay, so I can actually go back to this setting. Now, I also have sort of another problem, which is, what if on this path I have some unknown but unimportant edges? Well, why are they unimportant? If they are not important, it means that them being there or not does not change the connectivity of H. Well, this is because the endpoints of this unimportant edge are already connected by some other path that I've already determined. And that's why it is unimportant. So
necessarily in H. H.
Yeah. Everything here actually is in H. Yeah. Yeah, because the path and everything, it must be in H. I mean, of course, there could be some path that are going out of H and back in, but then H does not contain this information. So, yeah.
Okay, but if there are two paths like that, and both of them have an edge which is unimportant, then I mean, just changing one of them doesn't change again. You would have to change both. That's the definition.
No, I'm just picking a path, one of them, and we say, okay, so let's say there's an unimportant edge. Then the fact that it is unimportant for H, it means that there must be some other path of real edges.
Well, possibly.
Well, no, but between these two
but
points.
Why with real? Maybe also with unimportant.
Okay. I'm saying it must be real edges. Like you can continue this process and you must stop at some point.
With the path consistent with real edges.
Yes. This is because, I mean, H is finite. It's like k vertices. And if you manage to find another path at every point, and then all of them contain some unimportant edges, and you're just consuming vertices one after the other, the last one like is unimportant, then yeah.
The edge becomes unimportant exactly at the moment when you simulate with real edges.
Yeah.
Just stop.
Yeah. So I mean, yeah, it's just.
Okay, so this way you get a real path, yes?
Yeah.
Okay. I'm good, sorry.
Yeah, no problem. Okay, so basically this path is actually like a real path of determined edges, okay? And once I have this path, then it's pretty easy to actually determine these unknown important edges. How do I do that? I take, say, the lowest point. Sorry. First observation is actually V and Y are not connected to this path. Like no direct neighbors in this path. Why? Because if that's true, then these edges are not important, right? Because it's connected, right? Okay, so now I'm taking the lowest point on this path, and I'm going down one layer, just so that it's not connected to anything up top. Yeah, same idea. I'm going down one layer to get this non-connected stuff, and now I query this sort of thing. And this allows me to know if U is connected to V.
Wait, going down, but do we have that H is in a single layer?
No, I don't know. I just take the point in this path that is the lowest, meaning that it lives in the lowest layer with minimum I. I take this and I go down one step. Since it's the lowest point, if I go down one step, I know it's not connected to the stuff that are up top.
Well, but going down by more than one, because if you go down by just one, then you could have a just cross deep.
Yeah. Okay. So maybe I'm going a bit too fast. Yeah. Here, at some point we have to use this assumption that they live in these blobs, right? So I'm taking this private neighbor. If there's no private neighbor, then this point must be in a blob. Okay. Okay, sorry. Okay, so first here I'm assuming like an easy case where this lowest point is in the sort of the middle of this path. It is outside this blob, right? So when I go down, I take a private neighbor of this. I mean, if I don't have any private neighbor of this, then it must like for
neighbor is private with respect to someone else.
Yeah, with respect to like U and V. Okay. Because here I want to determine this edge between U and V. Okay. I mean, if it does not, then it must live in this block, and we will look at this case in a moment.
Oh, wait, but maybe this contained in the other way. Maybe U and V have a private neighborhood. This was the equivalence class over the neighborhood relation. So maybe this guy doesn't have an extra neighbor, but U and V has an extra neighbor.
Yeah, you're right, actually. So yeah, so you're saying that all the neighbors of this one is contained in the neighbors of U and V, right? It's contained in the neighbor of U and V. Okay, right, sorry. So this, if this is true, then it's on the same layer as U and V. Is that right?
Yes. Okay.
Yeah. So, yes, right. So, okay. So if it's on the same layer as U and V, then at my lowest point, I always prioritize U and V. And if there's a lower point, I take that one. All right, this is a little bit subtle, but I just wanted to start with an easy case, but
so among vertices on the same.
So if you have multiple vertices on the lowest layer, then and it's the same one as like U and V, then you take U or V. Maybe U, I think, yeah. U. And if not, then you just take one of them. As this lowest point where you drop down the layer and take a connected neighborhood and stuff. Is that okay? I mean, I will arrive at that case in a moment. It's the second case. But let's say that I have some vertex here with on a lower layer than everyone else. So it's just this idea of if it's lower, then I drop down one layer. I'm not connected to anything. It has private neighbor and stuff, and this is exactly what I want. And what do I mean by exactly this? What I want? Well, this is the case on the right here. You see, right? This vertex here has some connected subgraphs, and this edge is not connected to anything from the subgraph. So this is why, basically, if this happens, then it means that this is already determined. It cannot be unknown anymore. This is where I get my contradiction. So that's the idea. Now, yes, the other case where let's say that this lowest point is actually U or V, or then I prioritize taking them, and now now I should not have a problem, I think, because do I get my private neighbor? So you're saying that there might be a problem if the neighborhood of U and these neighbors of U and V also contains X and Y. Neighbors of U and V also contains X and Y.
The way I see it is that all the vertices on the lowest layer, there must be one that has a private neighbor.
Yes.
There's some partial order relation, and you take a min or max.
Yes.
So you can choose a guy who has a private neighbor.
Yeah, exactly.
You don't have a choice. It is you or not you. You can choose one.
Yes, because to say that I choose you, I have a problem because the neighbors contains all of them see X and Y, then actually I should have chosen X. Yes. Yeah. Okay, there's some several techniques in here. I promise the paper is well written. It's just that in the presentation, I didn't want to go too much into the technical details. Yeah. But yeah, the idea is just that you can find such a point where you can have some private neighbor drop down one layer and then determine these unknown edges. So which gives us our contradiction, right? So it was a little bit involved, but I hope that I convinced you that it should work, right? Right, so all of this is just to say that all the important edges, all the edges that might determine the connectivity of some subgraphs live all in one place. And now for each of these different blobs, then I can do something naive, like going through all possible subgraphs and then just keep the one that corresponds to my queries. I mean, the queries that intersect this blob. And this gives me some collections of graphs for each of these blobs. And now I claim that any combination of these collection of graphs will answer to all my queries. Okay, so finally, I have something that answers to our objective. So this graph that is mostly determined, and I have these numbers of different blobs, and in each of them I have like 2 to the d squared possibility, and I combine all of them. And anyway, my algorithm stays a polynomial in the number of outputs. Okay. So that's it for graphs with bounded maximum degree. And all of these things, skeletons, important unknown edges, these are new notions that we introduced, and we believe that is sort of like the right way, let's say, to look at these sort of problems. And we hope that this will be reusable for other reconstruction problem with this sort of setting. So what am I doing right now? I mean, with respect to this project, we are also working on some other stuff. Well, not exactly with the same co-authors, but I have some research group working on this. And what are we working on? So let us go back a little bit and forget connectivity for now, and just take a look at the setting of queries on K-sub graphs. What we're doing is that we're querying a K-sub graph. So we give some set of vertices to this oracle, and this oracle answers something. In this case of connectivity, the answer is basically, for example, here I just took 3 vertices. Say, if it's connected, then it's isomorphic to this or that. This E3 or a triangle. So if you look at this in a more abstract way, then this oracle on connectivity is just a partition on the K-subgraphs, yeah, up to isomorphism. So you're querying it something, and it returns a part. You say you're in this part. Like your subgraphs is isomorphic to one of these elements. So, for example, number of edges is just, well, in this case, it's like singletons, but this is not always the case if you have more like bigger graphs, of course. And then you can imagine like any other partition, right? So you can look at this setting of queries on K-subgraphs as just you have some partition of the graphs on K-vertices. And when we have these partitions, and one thing you can easily observe is that, let's say that I have determined that triangle-free graphs are unique when I have connectivity queries, right? If you look at my last partition, then this partition is sort of better than connectivity, right? Because I have the same part here. And then in this part, where these two graphs are clumped together, I can actually distinguish them. So I get more information. Now, this can be defined more formally, of course, as a partition refinement. So we say that, let's say, take two partitions. We say that one is finer than the other. Here I'm defining some partial order. Yeah. So my partition P is finer than P prime if I take any part of P, there exists a part of P prime that contains it. Yeah. So, for example, number of edges is finer than connectivity because I take anything like here, for example, this one, well, I have a part here that contains it. Right. So if we look at these queries from this point of view, then it's just some posets on partitions. And we would like to sort of say something more meta about these queries. Yeah, instead of saying, oh, okay, for connectivity queries, I can do this. For this exact query, I can do that. We would like to say something more like maybe there's a measure of fineness or like sort of like how much information it contains to say that if I contain enough information, then I can determine every graph uniquely, for example, big enough graphs, I say. Or maybe I can have an efficient algorithm to enumerate all graphs consistent with my queries. And for now, actually, we're just starting with like graphs of on three vertices. Like we're studying different partitions of these graphs, see what we can say about them. Yeah, I guess like in any problems, if you want to understand the problem, you start with small examples. Okay, so this is what we're currently doing. And for the future, well, first of all, from our connectivity problem, there's still this open question of NP hardness for K at least 4. I think this should be doable, even though I spend a lot of time on this and I have no idea how to do it. But I guess the same point is like, is this feeling of, oh, my research is justified only if this is hard, right? So if it's actually a polynomial in the general case, then why do we even look at particular graph classes? But we do believe that it is hard, just that we don't have a proof for it yet. And then maybe if it is hard, then take these new notions that we introduce, like the skeletons and stuff. Are there actually other graph classes with skeletons of small width? Because the reason why we look at triangle-free graphs with bounded maximum degree, is because they avoid these obstructions, right? Now, if we allow these obstructions to be there, then actually, can we do anything? Are they the only reasonable classes to look at? This is also another direction. We tried a lot of different things with not much success, but who knows? Yeah, who knows? You might have a better idea than we do, right? And then also, of course, this point of view on queries as partitions. Maybe there's some sufficient conditions on the partitions to, say, obtain a polynomial time enumeration algorithm or uniqueness for big enough graphs. And what are like sufficient conditions on partition looks like? Well, I was thinking about something like some sort of measure of fineness or like some measure of like the information that it contains. Recently, I looked at something like, so this is also very new to me, but like rank of partitions or entropy of a partition. Ideally, for example, we say that entropy is supposed to measure how fine the partition is and how much information it contains. So let's say that if it has high enough entropy, then we can always determine big enough graphs uniquely for or something like that. This would be like the best we can hope for. But of course, like this makes abstraction of any type of structure, graph structure, right? You're just saying something on the how the partition is. So maybe this is not true at all, and actually it depends totally on the structure that you can find inside these parts. In that case, then what are the good or bad structures to be sort of isolated in small parts for you to be able to determine anything about your graph? So of course, all of this is still very vague, but at the same time, these results are very new. So I hope that there will be much more to come in the future. Thank you very much for coming and listening to my seminar today.